Assalamu alaikum. Dear learners, I hope you are all fine. Today we are going to explore a very interesting technique called probabilistic roadmaps for path planning, which is commonly used for mobile robots. However, it may also be used for manipulators or stationary robots if you have complete grasp over its concepts. So let's first try to understand what this technique is and then how we can implement it on MATLAB using Robotic Systems Toolbox. As I have said in the preamble, that this technique can be used for path planning for mobile robots, but may also be used for manipulators. But you must work in the joint space of manipulators to use this technique. The reason being, in joint space, a manipulator is nothing but a point in an n-dimensional space, where n is the number of degrees of freedom. This technique will take the initial configuration and will provide a path that will take the manipulator to the final configuration. This seems quite easy, but for manipulators, defining the joint space is most of the time quite difficult. Because while representing the manipulator in the joint space, you must also represent obstacles present in the environment in the joint space, which is most of the time a very difficult task. So let's not get distracted. We are going to understand and implement probabilistic roadmaps in two-dimensional workspace of a mobile robot. So the task at hand is that we have a mobile robot placed at some starting position and it has to go to a certain goal position in a given map. In that map, we have walls, obstacles, and other kind of static hurdles. So on this map, all the areas where our robot can go are called accessible areas and are labeled with white color, whereas all inaccessible areas are blacked out. Therefore, we have what we call a binary map. Furthermore, depending on the size of the robot, our robot cannot access points very close to the walls and obstacles. For example, if this is our robot, then the accessible area are those areas where the centroid of our robot can reach. Hence, regions in the vicinity of the walls and obstacles will also be inaccessible. Therefore, we will have to mark all such regions with black color as well because they are inaccessible. This is called inflating the map because we are simply going to inflate or increase the size of the walls and obstacles a bit. The amount of inflation will depend on the size of the robot. So once we have generated the map, then next thing is to generate the road maps. Yes, this is where this technique gets its name. Just like the road network we have in cities, this technique is going to generate routes. For generating the routes, the very first thing is the number of nodes and their positions. You can think of nodes as intersection points of roads. So, firstly, specify the number of nodes are generated uniformly all over the accessible area of the map. After that, nodes are connected by straight roads, but whether a node will be connected to another node or not depends on the connection distance, which we must specify. Over here, we can either specify the connection distance or we can specify the number of nearest nodes that can be connected to a particular node. Normally, we go with the connection distance. Therefore, if two nodes are within a specified connection distance from each other and have no obstacle between them, then a road or a path will be generated between them. Generation of roads between all nodes complete the first phase of the path planning technique called construction phase. Now we know that from a particular node, which other nodes are accessible and can generate path between them. As the last stage of path planning, we need to specify the starting position and the goal position and query the Dijkstra algorithm for the path between starting and goal node. The starting and the goal position will be treated as two nodes on the map, just like all other nodes, and a path from the starting node to the goal node will be figured out using Dijkstra algorithm. We have already made a video on Dijkstra algorithm, so it is recommended to view that video if you don't know what Dijkstra algorithm is. Its link is given in the description as well. Dijkstra algorithm will return the shortest possible path connecting the start and goal node. So you will get the waypoints through which if your robot moves, it will reach a goal position from the starting position. Just before we move on to the implementation portion, you should have clear understanding that the number of nodes and their connection distance will dictate the density of the roadmap and hence the computational complexity. So if you have generated too few nodes, there might not exist any path between the start and the goal position. And if you have generated too many nodes, then computational complexity will increase too much. Similarly, specifying too large connection distance might not correspond to your physical robot, as it may not be able to travel too far in a straight line without localizing itself. And on the other hand, having small connection distance might not allow you to move from one node to the other. Typically, you must test different values of number of nodes and connection distances to achieve any optimal solution. I'll show you how you can consider and implement all these things on MATLAB using functions from Robotic System Toolbox. So let's move to the MATLAB environment and see how this technique can be implemented. So here is the MATLAB environment, and I have already generated an M file on which we are going to code some things. Over here, I have written 3 steps. Namely, the first step is load map and inflate it. So this is the first step which I have just shown you in the slides. After that, we will generate the roadmaps with some initial parameters. I'll show those parameters to you in a while. And as the last stage, we are going to query the PRM method to find a path. And finally, we will be showing that path over here. So for loading the map, we need a binary map. And I've already generated a random binary map which I have made on simple paint application. So as a very first step, I'm going to load the map, which is nothing but a binary image. And I have saved it with this name. Once I have loaded this map, the thing which the PRM method requires is not the map, but the binary occupancy grid. So I have to convert this map into a binary occupancy grid. That is, this map will be converted into a grid, and wherever there are accessible areas, that point of the grid will be turned white, whereas all others will be turned as black. So for converting it into a binary occupancy map, I'm going to use a binary occupancy map function and pass it with this variable which is named as b. And I have to specify the resolution which I want. 1 over here means that every pixel will be counted as 1 unit of distance. If you want to shorten up the things, you can use 2 over here or any other higher number. So, but for the time being, let us use 1 over here. So now let's just see that what we have in the map so that you have an idea that what we are dealing with. So this is the binary occupancy grid which we have generated. It is nothing but a map, and all the white areas over here are the accessible areas, whereas black areas are either walls or obstacles and are inaccessible areas. So once I have the map stored as a binary occupancy grid in my map variable, I need to inflate it. And for that, I need to first copy this variable into a new variable. So I'm going to use inflated map as a new variable, and I'm going to copy my old map into this new one so that my old map or the original map is retained. After that, I need only to use inflate function that will inflate whatever map you will provide. So I'm going to provide it with inflated map, and the amount with which I'm going to inflate it depends on the size of the robot. So if the maximum size of the robot is, let's say, 40 units, then I should inflate it by at least 20 units. So I can use 20 over here, or whatever is the size of your robot, you can use that number. So for the time being, I'm going to use 20. Now let's just see that what we have. So I'm going to generate a subplot of this size and going to show the original map in the first location, and then in the second location I'm going to show the inflated map. I have to place a comma over here. Now if I run this thing, let's see what we get. So this is what we have. In the first position we have the original map, whereas in the second position we have the inflated map. You can see that our robot cannot go very near these walls or these obstacles. So all these regions which are very close to these walls and obstacles are in fact inaccessible. So for the probabilistic roadmap technique, we are considering these regions as inaccessible. Therefore, over here, the walls and the obstacles have been inflated so that no nodes or paths are generated in these regions. So now we are going to use this inflated map later on. So we have the map, we have inflated it. The next thing is we need to generate the roadmaps with some initial parameters. For that, the very first thing is we need to generate a routine called PRM. So I'm going to use the variable PRM, and the function that will generate this routine is mobile robot PRM. So an object named as PRM will be generated, and now I have to specify some parameters. For example, the very first parameter is the number of nodes that I'm going to use. Let's suppose for starters, I'm going to use 50 nodes only. And for the connection distance between the nodes, I'm going to, let's suppose, use 80. And I have to specify the map as well, which I'm going to use. And for the map, I'm going to use the inflated map, which we have generated. So this is everything we need to do over here. So now let's just show that what PRM we have, what roadmaps we have generated with these parameters, that these number of nodes, connection distance of 80, and using the inflated map. So I'm just going to run this portion. There is a mistake of M over here, so I have used the capital M. I'm going to run it once again. Yes, this is the roadmap which we have generated. If you have time, you can count the nodes which we have generated over here. These will be 50 nodes, and they are randomly placed, evenly distributed all over the accessible areas. And all the nodes that have distance less than 80 are connected with each other. So you can see that for this size of grid, the number of nodes which we have used is quite low. And same is the case with the connection distance. But normally it is recommended to use a small connection distance and increase the number of nodes. Otherwise, your robot will have to move in very far straight lines, which is sometimes difficult. So we have generated the map, we have generated the nodes and connected them. Now we need to query the PRM method, and we need to specify the starting position, the end position, and we want the PRM method to figure out a suitable path from the start to the end location. So first of all, to specify the start location, I'm going to use theginput function, and it will take the coordinates of the mouse click as start location. So wherever I'm going to click for the first time, that location would be stored as the start location. So just to help the user, let me display over here that click for the start location. Similarly, for the end location, I'm going to display once again that click for the goal location. And I'm going to save this goal location in end location variable. And once again, I'm going to use ginput. So these two lines, this one and this one, these two lines are going to store two click positions as start and end location. After that, I'm going to query the PRM method by using the find path function and going to store whatever the path the PRM function finds in a variable. So the variable I'm going to use is simply path, and the function for query is find path. I have to give it the PRM method, the start location, and the end location. So that's it. So now let us see that what path PRM method finds. So for this portion, I'm going to execute this portion. This first line will show the roadmap, and then I'm going to click on these points to specify the start and the end location. So over here, you can see that it is saying click on the start location. So I'm going to click, let's suppose, over here. And now it is saying click on the goal location. So I can click somewhere over here. That's it. Nothing happened. And over here in the workspace, you can see that a path variable has been created, which is empty. So it means that there doesn't exist any suitable path between the start and the end location. So how can you be sure that the number of nodes you are using or the connection distance you are using is suitable for the map which you have? The thing is, we can never be sure. We want to use as few number of nodes as possible. So always start from a smaller number and then increment a bit in each iteration unless you find a suitable path. So how we can do that? I'm just going to write a small iteration function over here using a while loop. So while is empty path. So as long as the path is empty, what we are going to do, we are going to increase the number of nodes by let's suppose by 20. And we are going to update this PRM and we are going to query it again. So the path would be once again find path, PRM, start location, and that's it. And we should show whether we find any path or not. And we should also pause it for 1 second so that we can easily see what is happening. So this routine or this iterative routine is going to run as long as there is no path found. And for every iteration, the number of nodes are going to increase by 20. So there will come a time when there will exist some path. So after that, this loop will end and we are going to show the final PRM with the path over here. So that's it. Now let's just run this portion once again. We have to click for the start location. Let's suppose this is the start location, and we have to click for the end location. Let's suppose this is the end location. Now you can see that the number of nodes are increasing, and with every iteration the number of nodes are increasing, and that's it. We have found a valid path. You can see that this was our start location, this was our end location, and there exists this red color path between the start and the end location. And the PRM method has found that. So dear learners, I hope you have understood that how the PRM works and how you can implement this thing on MATLAB. This path variable can be used as a waypoint variable and can be given to any trajectory planning module so that your robot can move on this trajectory to go from the start location to the end location. So if you have any questions or any queries, I'm always there for you. You can reach me through my email contact or through YouTube comments. So have a nice day and take care.